This is the second part of section 10.4. We're going to work on multiplying radical expressions, and then we're going to work on dividing them and rationalizing the denominators. So we'll try to keep our work organized as we go through this, because sometimes these problems get a little bit longer. First one's easy. How do you multiply two radical expressions together? If they're the same root, just combine them together. So square root of 11 times square root of 7, nothing simplifies, so they're both square roots. When you multiply them, you simply get square root of 77. And we're done. For the one next to it, it's got terms on the outside and on the inside. So the ones on the outside we multiply on the outside, the ones on the inside we multiply on the inside. So 6x times 2 is going to give me 12x. Under the radical, 12x times 4x, 12 times 4 is 48. X times x is x squared. Now my question is, can I simplify the square root of 48x squared? I'll bet you I can. Square root of 48x squared, biggest perfect square factor of 48 is 16. So 16 times 3 gives me 48. The x squared stays over there. So I can rewrite this as 4x, right? No more radical sign anymore. Square root of 3. So now I get 12x times 4x square root of 3. 12 times 4 is 48. X times x is x squared. And the square root of 3 just stays. So it's a matter of keeping track of what's on the inside and what's on the outside. That square root of 48x squared could be simplified. The 6x times 2 are both outside terms, so they stayed on the outside. For number 3, this is a distributive property problem. So everything on the outside gets distributed to everything on the inside. So let's do this carefully. What's outside stays outside. What's inside stays inside. So I get a 4 square root of 77, because 7 times 11 is 77. Now, when I distribute the 4 and the square root of 7 to the second term, I get 4 square root of 7 times 7, which is 49. So I get 4 square root of 7 square root of 7 gives me 4 square root of 49. So here I get a 4 square root of 77. The square root of 49 is just 7. So 4 times 7 gives me 28. And it looks like I should be able to simplify that square root of 77, but I don't see any perfect square factors that go into 77. The only factors of 77 are 7 and 11, and both of those are prime numbers. All right, for number 4, we're going to have to FOIL this thing. So, again, the idea that if you multiply a radical by itself, it pops out of the radical. So what if I multiplied the square root of 3 times the square root of 3? Square root of 3 times square root of 3 is square root of 9, which is 3. The same thing will happen if I do, let's say, the square root of 7 times the square root of 7. I just did that, right? I got the square root of 49, which was 7. So when I multiply square root of 3 times 3 square root of 3, I get 3 square root of 3 square root of 3. Let's write it all out like that, and then we'll simplify it. For the outsides, I get a square root of 3 times a negative square root of 7, so I get a minus square root of 21. When I do the insides, let's do the insides carefully, because I actually have 4 terms that I'm working with here. I got a 2 and a 3, and I've got the square root of 7 and the square root of 3. So 2 times 3 is 6. Square root of 7 times square root of 3 is the square root of 21. And then the last term is going to be 2 square root of 7 times a negative square root of 7. So it's going to turn that plus sign on the outside into a minus sign. All right, let's come back to the first set of terms. 3 times the square root of 3 times the square root of 3, this is just 3. And 3 times 3 gives me 9. All right, so the square root of 3 gave me 3. Multiply it by the 3 that was already there, I get a 9. Look at these two inside terms. They're both square root of 21s. I have a 6 square root of 21 and a minus 1 square root of 21. 6 minus 1 is 5. So I get a 5 square root of 21. And then over here, square root of 7 times square root of 7 is just 7. So negative 2 times 7, negative 14. Which means I can simplify this one step further and combine the two constants. So 9 minus 14 is negative 5 plus 5 square root of 21. All right, so that gets a little bit more complicated. Maybe I should have given myself a little bit more space. But anytime you multiply the radical by itself, it drops the radical and gives you back the original number. Hey, number 5 should be a whole lot shorter. Look at that. We've got a square root of 8 plus 5 and a square root of 8 minus 5. Maybe you recognize that as a difference of squares pattern, which means our inside term should drop. So square root of 8 times square root of 8, same pattern as before, we just get 8, right? Square root of 64, which gives us back 8. The outsides and insides go away. I got negative 5 square root of 8 and positive 5 square root of 8. And then 5 times negative 5 is negative 25. And then 8 minus 25 gives me negative 17. Turns out it's a real number that has no radical expression in it. Interesting. All right, for number 6, square root of x minus 6 squared. We can do this one of two ways. I'll put on my other board, I got a square root of x minus 6 squared. So if you want, you can FOIL the whole thing out like this, right? Square root of x minus 6 squared means the square root of x minus 6 times itself. So when you do the first, the square root of x times the square root of x just gives you x. Do the outsides and you'll get minus 6 square root of x. Do the insides, you get another minus 6 square root of x. And then negative 6 times negative 6 is positive 36. The only thing I can combine are these two terms in the middle. So I get x minus 12 square root of x plus 36. The other option is to use that perfect square trinomial trick. When you take the first term and square it, so take the first term and square it, and you just get x. Multiply the insides by 2, so negative 6 times the square root of x multiplied by 2 will give you negative 12 square root of x. And then take the last term and square it, so negative 6 squared gives you 36. And you can see if you look down this column that I have the same answer that I got by putting them next to each other and foiling. I got x minus 12 square root of x plus 36. So perfect square trinomials show up in other places, and this is one of them. All right, then the last bit we've got to do is talking about rationalizing the denominator. Oftentimes I want a rational number in the denominator. So if I get an answer like 1 over the square root of 2, that's not rationalized because the number on the bottom is not a rational number. Rational numbers don't have square roots unless they're perfect squares, in which case you would simplify them. So if I had 1 over the square root of 4, square root of 4 is a rational number, it's 2. But the square root of 2 is not rational. So if I have a radical, multiply numerator and denominator by some value to make that denominator a perfect power, and then simplify it. The harder ones are what happens when that denominator is an expression like a plus b or square root of a minus square root of b. Then what you have to do is multiply the top and the bottom by the conjugate. So I got 6 examples, and we might work through all 6 of them because this takes a little bit of practice. So the first one is easy. I've got 7 over the square root of 2. Clearly the square root of 2 is not rational, but I can make it so very quickly by multiplying top and bottom by the square root of 2. So on the top, I get a 7 square root of 2. Remember we said that if you multiply a square root by itself, you just get the number on the inside, right? You get square root of 4, which is 2. All right, well, that was pretty easy. For the second one, what can I multiply top and bottom by to get that 12 to become a perfect square? I want to go for the perfect square that's closest to 12. I mean, I could be silly and just keep multiplying out, but what's the perfect square closest to 12? I'm thinking 36. So what happens if I multiply top and bottom by the square root of 3? Then on the top, I get a square root of 18y. On the bottom, I get a square root of 36x. But is that good enough? No, it's good enough for the number, but I'm still left with a square root of x on the bottom. So what if instead I multiplied by a square root of 3x? Well, now I get the 18yx on the top. That doesn't change much. On the bottom, I get an x times x, which is x squared. So we need to keep in mind both the variables and the constants when we do this. We've got an 18xy on the top, so let's leave that there for a second. On the bottom, square root of 36 is 6. Square root of x squared is x. Do we still have more we can do? Yes, we do. Up on the top, that square root of 18 breaks down into square root of 9 square root of 2, which is 3 square root of 2. So on the top, I can think of this as 3 square root of 2xy, and on the bottom, 6x, which really lets me drop that 3 top and bottom. And I get a square root of 2xy on the top and a 2x on the bottom. Now, warning, I can't simplify radicals and non-radicals together. I have a square root of 2xy on the top, I have a 2x on the bottom, but the term on the bottom is not under a radical. Only the term on the top is under a radical. So that's the best I can do. The key when I look at the answer here is that what's on the top, or what's on the bottom, does not have a radical on it anymore. The top can, that's not the issue. The issue is that bottom no longer has a radical. All right, I'm moving over to another board for number 3. So for number 3, the problem that was given was the cube root of 8y to the 4th over the cube root of 2x to the 5th. So I want to see what will make that bottom a perfect cube. Well, I know 2 to the 3rd is 8. So that's a perfect cube. If this 5th power were a 6th power, then that would be a perfect power also. So what do I have to multiply top and bottom to make that happen? Well, 2 times 4 is equal to 8. And x to the 5th times x is equal to x to the 6th. So it looks like if I multiply top and bottom by 4x, I'll end up with a perfect cube in the denominator. What I end up with in the numerator is not as much of a concern. I want a perfect cube in the denominator. So down the bottom, one big cube root. 2 times 4 is equal to 8. X to the 5th times x is x to the 6th. Up on the top, if I combine those together, I actually end up with a cube root of 32y to the 4th x. But you notice in this first expression, I can write this as the cube root of 8y cubed, cube root of y. And then that first piece becomes simply 2y cube root of y times the cube root of 4x. Let's combine those together on the top. So I get a 2y cube root of 4xy. On the bottom, everything comes out. Cube root of 8 is 2. Cube root of x to the 6th is x squared, right? 6 divided by 3 is 2. And the last step is just to get rid of those 2's. So I end up with a y cube root of 4xy over x squared. Now, these problems can be done in a lot of different ways. I could have multiplied those radical expressions on the top first and then simplified and broken them apart in perfects and not perfects. If I can simplify something first, oftentimes I'll do that because I think it makes the process easier. But if you got to the same answer I did, but you did it through a different process, then you could certainly do that. And the other thing you could do is you could have combined them together first, simplified the 8 and the 2, and then broken them apart again. All right, so more than one way to do these. All right, the 3 that are more challenging here are the ones where you have to rationalize the denominator. So look at the first one on the bottom, the x over square root of 7 minus square root of 5. I can't break this apart, right? It's a subtraction problem in the denominator, and so that minus sign means I can't just pull them into 2 pieces. There's got to be something more that I do to solve it. So the question is this, x over square root of 7 minus square root of 5. What we're going to do is we're going to reach back to that difference of squares pattern we saw before. Remember when we multiplied by that difference of squares pattern, we got rid of the radicals completely. The difference of squares pattern would say multiply top and bottom by square root of 7 plus square root of 5. And we have a name for that. We call that the conjugate. The conjugate of radical 7 minus radical 5 is radical 7 plus radical 5. Let's see how that works. On the top, let's just keep it the way it is, x times square root of 7 plus square root of 5. On the bottom, when we multiply these out, because now we're foiling, square root of 7 times square root of 7 is 7. Outside, inside, we'll get a square root of 35 minus square root of 35, so that goes away. Square root of 5 times square root of 5 is just 5. So this gives us x times square root of 7 plus square root of 5 all over 2. And that's my answer. You could distribute the x on the top, but it really doesn't help us at all. All right, so for this one, we multiplied top and bottom by the conjugate, and we were good. Let's look at another one. The next one that's on that PowerPoint is number 5. And it's a square root of 5 plus square root of 2 over square root of 5 minus square root of 2. So again, I can't break these apart because there's addition and subtraction signs in between. So I'm going to multiply top and bottom by the conjugate of what's on the bottom. All right, so I'm going to multiply by the square root of 5 plus square root of 2 on the top, square root of 5 plus square root of 2 on the bottom. And again, my goal is to get no square root expressions or root expressions of any kind on the bottom. Top is okay, bottom not. All right, we're going to have to do a little foiling here. On the top, square root of 5 times square root of 5 is 5. Square root of 5 times 2 is square root of 10. But because these are the same expressions, when you do the insides, you get another square root of 10. And then the last one, square root of 2 times square root of 2 is 4. Down the bottom, square root of 5 times square root of 5 is 5. When I do outsides and insides, they go away. I get a square root of 10 minus square root of 10. Those are gone. Minus square root of 2 times square root of 2 is 2. Keep going. On the top, 5 plus 4 is 9. Plus 2 square root of 10s. On the bottom, 5 minus 2 is 3. Now, if there were common factors that I could take out outside the radical, or if there are radicals that simplified, I would go further. I can't because there's no common factors between a 9, a 2, and a 3. All right, let's take a look at one more. This one's got variables in it. If I go back to number 6, take a look at that. I got a square root of x on the top and a square root of 2x plus square root of 3 on the bottom. And notice the way that radical expression on the bottom is drawn. The 2 and the x are both underneath that radical. All right, so I'm bringing my other board up. Clearly, I won't have space to solve in here. Square root of x on the top, square root of 2x plus square root of 3 on the bottom. Multiply top and bottom by something to get rid of that denominator, so I'm going to multiply by square root of 2x minus square root of 3. Concept is the same. The execution may look a little different because there's a variable in there, but it's all the same idea. On the top, when I multiply a square root of x times the square root of 2x, I multiply inside the radical, so I get a square root of 2x squared. A square root of 2x squared can actually be simplified as square root of x squared square root of 2, which will give me x squared of 2. So the x times the 2x gives me an x squared of 2. The square root of x times the square root of 3 just gives me a minus square root of 3x. Down the bottom, square root of 2x times square root of 2x gives me a 2x. The outsides and insides cancel. Square root of 3 times negative square root of 3 gives me a minus 3. And that's all I can do with that one. Right? On the bottom, I have a 2x minus 3, which is perfectly fine. And I've rationalized my denominator. So if it's something simple like, 7 over the square root of 2, then just hit top and bottom with the square root of 2. As they get more complicated, you start looking for what is the terms I can multiply the bottom by to get a perfect square, perfect cube, whatever outside index it gives you. And then for the more complicated ones where you have addition subtraction problems in the denominator, you multiply by the conjugate, which is the same expression that you started with, except you change the sign in the middle. And that's the end of this section. Actually, it's the end of this whole section 10.4.